All right. I'd like to thank you guys for coming and thank the organizers for giving me the opportunity to talk. So my research kind of focuses on three atmospheres, that of Earth, Mars, and the Sun. Largely, I'm interested in characterizing how planetary upper atmospheres respond to solar forcing. And so I look at the Sun and its variability in terms of in a more statistical nature. So what are common themes that reoccur in solar variability? The title of my talk is Progress Towards a More Physics-Based Approach to Solar Flare Irradiance Modeling. And jumping right into it, accurate estimates of solar flare irradiance are needed in order to estimate the atmospheric response to solar flares for both research and operational space weather applications. Solar irradiance proxy models, which determine the solar flare irradiance from a spectrally limited number of available measurements, are appealing because their computational simplicity allows for real-time estimates. And a couple examples of these types of models are the flare irradiance spectral model, which is used for research purposes. It's driven by the GOES soft X-rays, and so you can essentially produce a flare spectrum for any flare that's occurred while GOES has been making measurements. So that brings you back to the mid-1970s. There's also the GOES EUVS irradiance model for space weather situational awareness, and this is a new model that's driven by the new EXIS instrument that's on the latest GOES satellites operated by NOAA. And so its advantage is when it's fully online, should be able to produce solar irradiance within, I believe, one minute latency. The issue with flare proxy modeling is that it's relatively new, and the accuracy of current flare proxy models can still be improved, in part by incorporating more of the underlying physical processes known to determine the flare spectrum. And so here's an overview of the talk. I'm going to spend about 10 minutes presenting the FISM model. It's sort of the state-of-the-art model that we're working with today. And then the bulk of the talk is going to be discussing three recent developments that can aid empirical flare irradiance modeling by incorporating more physics into them. And then the last 5 minutes or so, I'm going to just discuss how these developments can be incorporated into recent models. FISM, or the flare irradiance spectral model, it's probably the most widely used flare irradiance model, and it models irradiance from 0.5 nanometer to 195 nanometers. It's been used to study the response of the Earth's atmosphere to flares, Mars's atmosphere to flares, cometary atmospheres, and lunar atmospheres to flares. So it's certainly seen a lot of use in the astronomy community. It was originally based on flare measurements from time T, and recently we've updated it with flare measurements from SDOE as part of the MAVEN mission at Mars. So MAVEN includes an EUV monitor that measures EUV irradiance in 3 bands, and we can use those bands to drive a version of FISM called FISM-M, where the M stands for Mars. So FISM kind of follows the lead of its predecessor models, like those from Henneregger and the UVAC model from Richards, where the solar irradiance is decomposed into a solar cycle and a solar rotation component. The innovation of FISM is it includes these flare components, where it has a gradual phase component and an impulsive phase component. The solar cycle component is just the daily average irradiance that's been smoothed to some number of solar rotations. For FISM, I believe we use 108 days, and so that gets rid of all the solar rotation variability, and that's the solar cycle component. The solar rotation component is the residual. So if you take the solar cycle component and subtract it from the daily average component, you're left with these residuals that capture the oscillations due to solar rotations. So here I'm actually showing in blue Lyman alpha irradiance at Earth, and in red that at Mars. And so this gives you an idea as to why we need an EUV monitor at Mars, because there's only once every 2 years where the planets are lined up and the solar rotations, the modulations from solar rotations would be in phase. Typically the solar cycle and solar rotation components are from some commonly available daily average measurements like F10.7 magnesium-2 or Lyman alpha. And here's an example of what the different flare components look like. So the gradual phase component is this second portion here, and the impulsive phase component is obviously the more impulsive component. And so the actual flare radiance is a superposition of those two. The gradual phase is determined as, from a power law relationship between EUV irradiance and soft X-ray measurements, and the impulsive component is from a power law relationship between EUV irradiance measurements and the derivative of the soft X-rays. So we're invoking the Newport effect here. So there's very little explicit physics in the model. We do leverage the Newport effect for the impulsive phase, but implicitly, the fact that we need to decompose the solar variability into a solar cycle and a solar rotation component is due to physics of what's going on in the sun, namely that the quiescent and active region coronal plasmas or solar plasmas are going to be forming at different temperatures. So the latest version of FISM-M was calibrated with 431 M-class or larger flares measured by SDO-EVE in the 6 to 37 nanometer range, and 66 flares in the 37 to 106 nanometer range. And the reason for the difference is that longer wavelength channel of EVE is run at a much lower duty cycle to minimize instrument degradation, so it observed fewer flares. One thing that FISM is really good at is at predicting the average flare radiance, because it's a statistical model that relates soft X-ray magnitude to EUV magnitude. You can use it to compute average spectra for a particular soft X-ray magnitude. And so down here, I'm showing the average enhancements for C5 and M5 and an X1 flare, and then in terms of percent enhancement in the lower panel. And so this type of exercise is nice because it can give you some numbers to carry with you as to how much irradiance do we really have in a particular flare. And so if you look at an X1 flare, the integrated irradiance from 6 to 106 nanometers is about 15%. And so if we compare that to the total increase over the last solar cycle in the same band, that was about 50%. That lets you know that an X1 flare is going to get you about a quarter solar cycle worth of variability in a matter of 10 minutes to an hour. If you looked at about an X5 flare, you get a full solar cycle's worth of variability over a matter of a few minutes. One thing that we also noticed when we were looking at average flare behavior with FISM is that the limb flares are systematically dimmer, even for hot coronal lines that we typically consider to be optically thin. And you can see that here where I'm plotting how much brighter disk center flares are versus limb flares for the flares that we use to train the FISM model. And I just want to draw your attention to this region here. There's a lot of mostly optically thin lines here below 20 nanometers, and we still see that the flares that occur near disk center are systematically brighter. And that's something that I'll go into a little bit further in this talk. The FISM daily average uncertainties are actually, I think, really, really good. It can reproduce the SDO-EVE daily average irradiance to within 3 or 4%. This figure here shows the model uncertainties driven by the 3 different bands measured by MAVEN. There's a Lyman alpha band, a band from 17 to 22 nanometers, and a band from 0 to 7 nanometers. And so you can see that obviously you'd want to pick the model that has the lowest uncertainty. So for most wavelengths, the 17 to 22 nanometer band is the ideal model. But in certain regions, Lyman alpha becomes the better candidate, and that's where you would expect it. So for the hydrogen continuum and the helium continuum, and then the bright helium 304 line, Lyman alpha tends to be the better proxy because it's formed at similar temperatures and similar regions in the sun's atmosphere. There's also regions here where the uncertainty is huge, right? And so the reason for this is there's really just very little signal here. And so if we were to overplot the solar spectrum with the uncertainties, you'll see that the uncertainties increase between the lines. And so we're seeing as a large error on a very small signal. And in terms of integrated irradiance, it's actually quite minimal. On the other hand, the FISM flare component uncertainty is quite large. And the simple reason is that soft X-ray emissions are weakly correlated with EUV emissions. And this is kind of what the aim of the work we're doing now is to try and correct this. This is the uncertainty as a function of wavelength for a flare, an X2 flare that occurred in October. The dashed line is the pre-flare, and so that's around 4%. But if you look at the solid line, that's the uncertainty at the flare peak, and you can see in many of these lines, the uncertainty exceeds 100%. So to accurately, so FISM can't accurately predict the irradiance for any particular flare. I think it can give you an idea as to what an average flare is going to look like, but for doing single case studies, there is going to be a lot of uncertainty in the predictions. And so what are the big known issues with FISM? So there's soft X-ray irradiance is a poor EUV proxy. What I haven't talked about yet, but I will talk about in this talk, is that the time lags aren't accurately captured. So FISM assumes every EUV line is going to evolve like the soft X-ray lines and the soft X-ray emissions in time. And so here are 3 different emission lines measured by Eve in black: iron 23, iron 19, and iron 16. And the black is the Eve measurements. The blue dashed is the time profile that FISM would predict. And then the red is a model I'll talk about later. But if you just compare the blue and the black, you can see that, especially for these cooler forming lines, FISM isn't getting the time when the intensity peaks right, and it's also underestimating the entire width of the profile. And so in doing so, it's going to underestimate the total energy that's being released from the flare. And then finally, the limb darkening isn't fully understood. And so those items are what I'll be talking about next. I'll start by using the soft X-ray emission measure instead of the soft X-ray intensity to predict EUV intensity. And so here, whereas the idea that EUV emissions are going to be proportional to soft X-ray emissions isn't really based on really any physics at all. We do know that the intensity is proportional to the emission measure, where the proportionality constant is the contribution function. And so if we make the assumption that for hot lines at least, that the volume of plasma that we see in the soft X-rays is the same as the volume of plasma that's creating the EUV line emissions, we can approximate that the GOES peak emission measure is going to be equal to the peak emission measure for EUV lines, at least for some hotter lines. And so we went to take a detailed look into this, and we selected lines that form at temperatures that GOES is sensitive to. And so these are going to be relatively hot lines. And spectrally pure lines, so lines that contributed to 80% of the Eve resolved signal or more. What we found was we had to separate the flares into their location on the disk, that there was a center to limb variability that we needed to account for. So here are the lines that we looked at. We looked at an iron 18 line, an iron 19 line, an iron 21 line, an iron 23 line, and then 2 iron 24 lines. And these scatter plots show the irradiance versus the emission measure, where the color code, where red corresponds with the limb flares and blue corresponds with the disk center flares. If we look here at iron 24, so these are going to be the hottest lines. On each panel, I've put the Pearson correlation coefficient. You can see they're quite high. There's really good agreement for the hottest lines. And then if you look at the cooler lines that we analyze, these iron 18 and iron 19 lines, we see that the correlation coefficient is around 0.9 versus near 1. So we do see that the correlation decreases with formation temperature. And this is kind of what we expected. We knew that there was going to be some limitations to the assumption of using the GOES emission measure as a proxy for the emission measure of the plasma that's emitting these lines. Another thing I want you to notice is that in each case, the the limb flares were systematically dimmer for the same emission measure than the disk center flares. And that's going to motivate the next part of this talk, which is predicting opacities to account for flare limb darkening. So first, I guess we should ask the question, should we even expect to see flare limb darkening in lines that are typically treated as optically thin? The answer is yes. When you realize that the plasma density in a loop during a flare increases by 10 to 100 times that during 10 to 100 times of that occurs during an active region loop, you will see some lines that are typically considered optically thick become considered optically thin become optically thick. And we can illustrate that with a simple 2D model of a loop, and it's simulated using a radiative transfer code, where we are essentially allowing for the photons to resonantly scatter within the loop. If we look at this top panel here, this is a loop that has active region plasma densities. We have an observer located here, 45 degrees off the apex, and the color indicates the amount of photons that are reaching an observer at that position. So white indicates the observer sees all of the photons, and black indicates that the observer does not see that portion of the loop. And so in the case of the active region loop, the observer over here can see the whole loop. The far leg appears a little bit dimmer, but certainly it can be resolved. And the total integrated reduction in signal is about 3%. So in this case, the optically thin approximation holds. Now, if we take this same loop geometry but increase the density by a factor of 30, so it's comparable to what we would expect for flare densities, and now we put the observer at the top of the loop looking down, we can see that the observer can certainly see the outside shell of the loop, but photons emitting from inside of the loop are going to become attenuated, and certainly at the foot points, the foot points are becoming invisible to an observer located at the apex. If we move the same observer over by 45 degrees, the far leg of the loop becomes completely attenuated. And so the total integrated signal from this loop is going to be markedly lower. We can do this exercise for a continuous range of observing positions and calculate how much the signal is going to vary when the same loop is varied off the apex. And located for an observer located at 45 degrees for this loop, it's going to be about 20% dimmer. And for an observer located out here at 80 degrees, so out here at 80 degrees, it's going to be about 37% dimmer. And sure, this is a simple approximation. A loop is never going to be perfectly equatorially oriented, which this would require. But there should always be some equatorial component, at least within the Joy's law approximation. And so there will frequently be a portion of the loop or the arcade that is going to be obscured once the plasma densities reach that of flare plasma. Yeah.
This is a 2D model.
That's right.
So in 3D, I would expect this to be much less of a problem. Is that right?
Well,
usually you'd be looking at edge on, right? So you can still see the arc.
Perhaps. So I think there is going to be an equatorial component, right? So so this would apply to the equatorial component of the loop. Also, if you have an arcade, the same principle would apply to an arcade where, let's say you had an arcade that was oriented equatorially, that as it approaches the limb, that far side of the arcade is going to be somewhat attenuated from the near portion of the geometry. But you're right, it is a simplification, and it's going to change somewhat in 3D. I'm not entirely sure if it probably would be less so.
I think this would be the worst case scenario.
I think you're right. Yeah. Okay, and so now we're going to expand on the emission measure proxy analysis to characterize flare limb darkening. So we looked at 300 M-class or larger flares measured by the 6 to 37 nanometer band of Eve, and we split these into groups of about 40 according to their location on the solar disk. And so we know that the intensity at the source is related to the emission measure by the contribution function. If we assume that there's going to be some self-absorption in the corona, which we can lump into this extinction factor, what we measure is related to what's emitted according to this expression here. And so now we can substitute I naught into this expression, and we're left with our measured intensity being related to our measured emission measure is related by the product of the contribution function and this extinction factor. And so we can lump these two terms together, and so the measured contribution function has this extinction factor lumped into it. And so we can take a group of flares that are located at some angle off disk center theta c and find this measured contribution function. And we can take another group of flares that are located some position theta L off disk center and find another measured contribution function. And if we take the ratio of those two, everything divides out except this term here that's related to the difference of the opacities for the two different geometries. And so we can do this exercise for 6 different lines at 5 different positions. And so here I'm plotting the ratio of the extinction factors as a function of angle for the 5 different lines, and these are the same lines that I showed in that emission measure study. And if we just look at, say, the hottest line at this iron 24 line here, you can see that as we move off disk center, the ratio of the extinction factors increases, and so the flares get systematically dimmer as we approach the limb. And it happens to some degree for all of the lines that we looked at. And so now we can rearrange this same data, and now we're plotting it versus wavelength. And so the color code corresponds with the position on the disk. And if you look at any one particular angle, any one particular color, you don't see any real function of wavelength. So it's not quite that simple. And so to really understand what's causing the different lines to limb darken differently, we have to really dig into the physics of what the opacities depend on. And so delta tau remembers that expression that shows up in our measurement. So we can measure delta tau. If we write it in terms of its physical parameters, it's equal to the change in the ion column density times the resonance scattering and cross section. And so each of these we can write out. We can write the ion column density in terms of electron column density times some abundance factors, and we can write out the resonance scattering cross section in terms of its atomic physics parameters. And so we've got a whole bunch of terms here that we essentially can look up and know in advance, except for this electron column density. And so we can lump all these factors into various constants, except we keep one wavelength term, and we keep this electron density term. And the reason that we do this is we can now divide both sides of the equation by eta and this Greek letter here, which I can't remember right now. And so it allows us to actually measure the average change in the electron column density. And so here's our measurement. And so we can take the natural log of our measurement to isolate the delta tau and multiply it by some factors. And so if we essentially plot this term on the left that we can measure and calculate time as a function of wavelength, we should get the average increase in the electron column density along the line of sight. And so we did that for the 5 lines. Here's just 2 examples of what that looks like. So this is the group that was furthest on the limb, located at 73.8 degrees. And this is the next furthest group at 60.9 degrees. And just to make sure everybody's on the same page about what we're actually measuring, so here if we have a red eye observer looking down on a loop and a blue eye observer looking over at a loop, the average, and we're just concentrating on a source of emission located right here, the average increase in column density is going to be this little segment here. Of course, this is going to be averaged over the entire loop. So this is just for one infinitesimal portion of the emitting source. Okay, so now we can do this for the 5 lines that we have, and we can plot the increase in the change in electron column density as a function of distance from from disk center, and we see it increases. Here I've just plotted a line, but from that simple 2D model, it did look like it had some shape to it. There was perhaps a quadratic might be a better fit, but with 5 points, I feel like a line is an okay fit there. And so what can we do with this? So first, we can do a sanity check. The change in column density is going to be due to a change in spatial scale. And so we can calculate what that spatial scale would be for a typical loop. And we find that it's between 0.4 and 4 megameters. And we can compare that with images of typical active region loops. And those spatial scales are between 1.5 and 6 megameters. So these numbers work out all right. Of course, we're not going to use Eve to actually measure the size of flare loops when we have AIA. So this is sort of just gee whiz, but it doesn't really do anything useful for us. But we can do But what is useful to do with this is that we can now predict the line opacities for any line, because once you have the change in electron column density, you can compute the change in ion density. We know what the resonant scattering cross sections are, and so we can do simulations we can simulate flares and see how the opacity evolves as a function of time. And so we did some of those simulations that did just that. And here's an example showing the change in opacity as a function of wavelength at the peak of a canonical M-class flare. And I've drawn in where tau equals 1. And so you can see that a number of these lines exceed the optically thin limit and start to become somewhat optically thick. And so I want to, let's see, how much time do I have? I'm going to just jump through this real quick because there's some more stuff I want to talk about. But what you can do with this simulation is then you can simulate how particular lines evolve as a function of time, as far as their limb darkening. You can also model how the limb darkening over particular bands evolves over time. And so here I've taken the AIA bands. They're all color-coded here, at least the EUV bands. And I'm plotting the percent limb darkening as a function of time. And so you can see this value here is 30%. So a number of the bands will be about 30% dimmer when that flare occurs near the limb versus when it occurs near disk center. But more importantly, they don't limb darken in tandem. And so certain lines are going to limb darken more than others and at different times. And so if you're doing studies that are using AIA filter ratios or Eve line ratios, and you're studying flares, and you're not accounting for the fact that the optically thin approximation is breaking down, you're going to get different results in your predictions of temperature and plasma density if that flare is located at disk center versus whether it's located at the limb. Okay, and so the last thing I want to talk about is considering a simple flare cooling model to account for the EUV gradual phase delay. Okay, so it's well known that light curves from relatively cooler forming coronal lines tend to be broader and peak later than those from hotter lines. Here's an example of this effect. Here at the top is the GOES flare temperature, and then we're looking at successively cooler lines, light curves from successively cooler lines as we go down the figure. And you can see that as the plasma cools, the corresponding light curves are going to peak at a later time and be somewhat broader. And the simple fact is that typically when we're looking at flare light curves in the EUV, that plasma is largely in a cooling phase, and so it's simply just cooling through the bands, through the formation temperatures that particular lines are sensitive to. This presents a challenge for flare irradiance modeling, which may only have a single measurement, and so if we're just using the GOES XRS to predict all of these light curves, we need to somehow have a time-dependent function that modifies it accurately. We showed in a 2017 paper that a simple lumped element thermal model can be used to accurately predict EUV light curves from the GOES broadband light curve. And so because lumped element thermal model is a lot to say, we call it LETM for short. And so it's a heat transfer technique where thermal resistances and capacitances are collected into single terms. So essentially, it's just a way of rewriting the Cargill flare cooling model. So if we start with the Cargill model here, we've got the heat flowing into the loop, the heat being radiated from the loop. So we're assuming it's in a purely radiative cooling phase. And then we've got a thermal capacitance. And then we've got temperature. We can eliminate temperature by defining a radiative resistance to heat transfer. And so the temperature and the radiative resistance are related to the radiative cooling term according to this expression here. And we can relate the radiative resistance to the plasma parameters with this expression here. And so we can substitute temperature for the product of the radiative resistance and the radiative cooling term. And so we've eliminated temperature from the expression. And the next thing we want to try and do is squeeze out this thermal resistance out of the derivative. But we can only do that if it's varying slowly with respect to the cooling term. And so we can define a quasi-static ratio. And when this is much larger than 1, it means that the radiative resistance term is varying slowly relative to the cooling term, and we can factor it out of the derivative. And so we tested this for one flare. Raftery and others looked at a canonical flare with I think it was a canonical C4 flare that they looked at with EBTEL. And so we used those results and expanded on them to calculate how this quasi-static ratio varies over the course of the flare. And so here's the flare temperature, the flare emission measure. Here's the energy being radiated from the flare. Here's the radiative resistance, and then here's the quasi-static ratio. And I've drawn this line where it's equal to 2. So I'm going to call 2 much larger than 1. And we see that it gets really big here, and this region where it gets really big is also right between the formation temperatures of iron 19 and iron 16. So it's right where these EUV lines are forming. And so at least for some cases, we can pull out the resistance out of the derivative, and the product of the thermal resistance and the thermal capacitance is the thermal time constant of the loop. And this is the exact same that Cargill found when he was looking at the radiative cooling time constants. If you were actually to write these out in terms of the plasma parameters, they'd be the same. And so the next step is we want to get rid of the heat the energy being radiated from the loop, and so we argue that for a radiative cooling loop near the formation temperature of a particular line, the energy being radiated from that loop is going to be proportional to that line intensity. And so we can now substitute in line intensity into the equation and a proportionality constant. And so now we're gonna do a little hand waving, and you'll have to bear with me here. But I'm totally aware I'm waving my hands. So we're going to assume the excitation rate of transition IC, the excitation of it into its excited state, the rate that it's being put into its excited state is proportional to the emission rate of some hotter line, IH. And then we're also going to assume that since we're now relating two hot EUV lines, that the system time constant is equal to the line time lag. And so after we collect all our constants into the intensity of a hotter line and the intensity of a cooler line, we can normalize it by the intensity of the hotter line, and all of the other proportionality constants fall out. And so the idea is, can we take some hotter line measurement and the time lag and solve this equation for the cooler line and get something that involves with time like an actual cooler line does in reality? And so here's three line measurements: iron 23, iron 18, and iron 15. And I've indicated the time lags between the iron 23 and iron 18 line, and then the iron 18 and the iron 15 line. And so if we use this red light curve as our IH and this first time lag as our time constant, and then solve this equation for IC, we get this green curve here. And then if we now take this green curve here and put it back in the equation for IH, and then use our second time lag here, we get the blue curve. And it turns out that it agrees remarkably well with the observations. And so we went and looked at over 1,100 flares that were C5 or larger measured by SDO-EVE, and found that this relationship holds for the majority of flares. Here's 4 more examples. And in the paper, I think we have a total of 8 other just case studies that we showed. But we wanted to try and convey how well it works by doing a statistical study of the entire data set. And so what we used as our figure of merit was the model measurement variance. So that would be the difference between the model predictions and the EVE measurements. And we compared the variances when the LEDM technique was applied to the variances that we got if we didn't apply anything. And so this would be more like a FISM-like model. And so here's the status quo variances. So this is like a FISM-like model. And then here's the LEDM-like variances. And you can see that they're smaller by a factor of 2 or 3. And then we found that if you used a cooler line that was closer to the, if you used 2 lines that were closer in temperature, you got even better agreement. And so we used the iron 18 line as well. And so back to the hand waving. There are some missing pieces. We were able to derive this fairly directly, but the equivalence of the heat flow into the system and its relationship to the line intensity, I think, was certainly the argument was an approximate argument. But what it seems to be saying is that in the cases where this relationship holds, the energy exciting the cooler line is apparently proportional to the intensity of the hotter line. The other issue is the equivalence of the thermal time constant to the time lag, and why that might be is still unclear. So there's certainly some missing pieces. Some missing pieces remain, and the above approach may be entirely off base, but there's overwhelming observational evidence that the flare light curves from a warmer and a cooler line are related by a single number, which is the time constant, which I think is physically curious, And as far as if you're just interested in improving models, it makes it much more convenient. Okay, and so now I'm going to spend about 5 minutes talking about how we can roll these new effects into research and operational irradiance models. So we presented 3 physics-based advances to address 3 current shortfalls in empirical flare irradiance modeling. I think the emission measure proxy was pretty straightforward, and it can improve the predictions of the flare peak magnitude, but it doesn't provide any light curve shape information. The center to limb variability correction accounts for the limb darkening of coronal emissions. And the LEDM method can improve predictions of how light curves evolve in time, but it provides no information of the flare magnitude. And so you could use improvement 1 to get to improve the accuracy of the magnitude, and improvement 3 to improve the accuracy of the time evolution of the light curves. So I guess I didn't say this earlier. It was on my slides, but I didn't read it. And so the problem is, to use this method, it hinges on the ability of being able to predict the time lags in advance. So in everything that we showed, we measured the time lags from the data, and then using that single number, we're able to reproduce the light curves. And so without being able to predict what the time lags are, we're not able to actually implement this method. We did try simply assuming that the EUV lines were going to typically peak at the GOES temperature prediction, and that doesn't work really even a little bit. I think the oversight was that the time when an EUV line peaks is going to be related to its formation temperature, but it's also going to be related to the emission measure. And so I think we should go back and do this analysis and take the emission measure into account. Okay, and so then what do we need to do to get these into the models? Incorporating the emission measure proxy using the GOES XRS is straightforward, and that looks like it'll work for hotter lines. We still need to look and see how much it'll improve the model uncertainty for cooler lines. We do know it breaks down for cooler lines, but it still might be better than just using the soft X-ray intensity directly. But ideally, it would be good to have an emission measure for the cooler plasma, and we might have that with the GOES Exis measurements. The issue is that the lines that Exis are measuring are fairly widely spaced in formation temperature, and so there may not be enough overlap to get a good emission measure out of the GOES out of the Exis measurements. Incorporating the center to limb variability correction can be implemented by computing the line opacities with Chianti for a given flare location. Then the resulting extinction factors can be applied to irradiance predictions. And so this really could just be an add-on to any model, something that is computed at the very end, at the very last stage, and the extinction factors are just applied to the predicted irradiance spectrum. And then incorporating the LEDM light curve estimation hinges on the ability to predict the EUV time lags, which has yet to be done. And so we need to find a method to predict the time lags. We have some ideas on how to move forward. We just haven't implemented that yet. And as I was talking, I realized there was an important caveat to the LEDM technique, and it's that it doesn't predict long duration events well at all. It doesn't capture the delay in long duration events. And I think the reason for that is this whole framework assumes isothermality, and that's going to really, it'll break down for any real flare, and it's going to break down even more for a long duration event. And so unfortunately, those can be, at least when they are large, some of the most geo-effective flares. But that's all I have. So I'll just leave up the references that I cited, and take any questions if I have any more time. Thank you.